superpositionality and quantum entanglement, among other things. And so over to you, Rajni.
Thank you. Yes. I'm not able to share my screen. Hello.
Yeah, you can share your slides.
It shows like host disabled participant screen sharing.
Oh, okay. Just a second. I think we need to make you the co-host. Just a second. Okay. And can you share the slides now?
Yeah.
Are you able to?
Yes. Yes. Yes.
Okay.
Just a second. So is my screen visible?
Yeah, you can start.
Okay. Yes. I would like to start by thanking the organizers of Quantum Information and Quantum Technology 2023 to provide me with this opportunity. Yeah. So today I am going to present one of my work, namely boosted quantum and semi-quantum key distribution. This work is done in collaboration with Surya Thana and Professor Vijay Shankar at IIT. This is the brief outline of today's talk. For pedagogic purposes, I would like to start with what is secure quantum communication, and then going over to quantum and semi-quantum key distribution. Afterwards, I will come to my work, which is boosted QIQT and SQKD. Yes, okay. So the communication in a secure manner has always remained a task of primordial importance, and there have been many efforts to design various ciphers for the same. However, in 1926, Vanam had given an encoding scheme. The cipher is popularly known as the Vanam cipher and is also called one-time pad. So, uh, the idea was to use the XOR operation between the message and the key. So, given a message and key, in this way, one can get the corresponding cipher text, and whoever is in the position of key can performing a reverse operation over the key, and the cipher can retrieve the messages back. The the main reason behind the popularity of this encoding scheme was this encoding scheme was shown to be unconditionally secure. However, there were some conditions. For example, key should be as long as the message. It should be perfectly random. It should be only used once. As long as these conditions are respected, this OTP is shown to be unconditionally secure. So, given this, the task of secure communication basically reduces to the task of secure key distribution. And that takes us to what key distribution schemes are considered nowadays. So whatever is used with today's systems is based on the computational complexity. For example, there have been RSA cores, there have been data encryption schemes. However, since all these schemes are classical, so Eve can always monitor the data, and the other conditions which are forced over these systems is due to technological advancement. So technological advancement have always you know, shown to break the code of a sufficient length. So the constraint comes on having the larger and larger length keys. The other thing which leads to the question mark over this scheme is the discovery of this quantum algorithm that can decrypt the messages in the same time as an encryption. So these two features have really focus really taken us to ask the question like the security of the system should be given by some laws of physics, and that is what take us to the quantum key distribution. So when we say like we have a quantum key distribution that provides the security of based on the laws of physics, so one can always ask the question, what extra does it provide with respect to classical cryptography? So with QKD, one can always able to detect the presence of E. So that is a distinguished feature which was not there in classical cryptographic task. So going over to QKD, so when one wants to distribute random and a secure key between two participants, so what are the two essential requirements? So one is a correlation. This ensures that the key which is being shared between the two participants should be identical, and the other is randomness. This randomness is requested so that one cannot uh, know priori like what is the action we are going to take. And then we move over to the fundamental question of QKD is how will Eve be detected? So thanks to no cloning theorem given by Wouters, which says that one can always perfectly clone to orthogonal state, but however, as long as one have non-orthogonal state, they cannot be perfectly cloned. So for example, here 0 and 1, which are supposed to be orthogonal, one can always clone these state, but as long as we have alpha 0 plus beta 1, so what we will get is some sort of an entangled state and not the exact copy of the state. So this no cloning theorem plays an essential role in providing the security to the QKT protocol. Okay, now we will discuss the BB84 protocol, which is the first ever QKD protocol. So it assumes there are two participants, and when we say two participants, we mean two intending participants, namely Alice and Bob. Uh, Alice is supposed to prepare the quantum states. In particular case, these are supposed to be qubits, and Bob is the one who performs the measurement. So it is suppose like Alice have two mutually unbiased bases shown here by this color coding. So black is corresponds to the 0 and 1 corresponds to the computational basis. The red states corresponds to the states of the eigenstate of sigma x operator. And Bob also have the same two basis choices to perform measurement. Channel is supposed to be noiseless, and Alice will randomly prepare one of the states and she will send it to Bob. Now, whenever this color coding match, or I mean, whenever the choice of basis for Alice and Bob matches, uh, one always get a perfect correlation between the input and output. So, uh, uh, one bit of information is being shared. So this can be seen as like whenever the basis choices matches, that will be used for key generation and for security checks. And same is here. But whenever the basis choice doesn't match, one cannot infer what was the thing which was sent. So that those rounds have to be simply discarded. This particular thing results in the key rate of a 0.5 bits per transmission. However, what are we losing is like we have to discard at least 5% of the data. With this, that was all about BB84 protocol, and these are some other protocols, like the seminal protocols, which are which are also given experimental realizations. We now focus over the semi-quantum key distribution, and I'll start with why it is important. So this SQKD, the idea of SQKD came from a question which was asked by Boyer in 2007, that can we have quantum key distribution if there is only one quantum participant? Please note that there were two quantum participants in case of a BB84. Now, why this question is important? So this question has both theoretical and a practical importance. Theoretical importance comes from the fact like what minimum quantumness one required to perform a particular task. In this particular case, the task is of a quantum key distribution. The practical viewpoint comes from like ultimately one will have to distribute information in a large number of a participant. And if every participant is a quantum, it requires to have quantum resources at each participant's end. So that uh, increase the burden of availability of quantum resources in today's noisy intermediate quantum devices era. So the idea of SQKD reduces that burden. Given this, we now define what do we mean by quantum and the classical participants. So quantum participants who have access to all possible quantum resources that can prepare any quantum state that can measure in any basis whatsoever. However, classical participant can only measure in the computational basis. So given this, we go over to the semi-quantum key distribution protocol. So similar to the BB84 protocol, it is assumed like we have to intended participant, Alice and Bob. Alice, being the quantum participant, can prepare state in any of the two bases, either the sigma Z or the sigma X. However, since Bob is a classical participant, he can only measure in the computational basis. The channel is again assumed to be noiseless. Uh, However, when we started discussing, we saw we had a requirement of a randomness. So we are having a perfect randomness in terms at the Alice end, but at the Bob's end, there is only one fixed choice, which is of measuring in the sigma Z basis. So to introduce randomness at Bob's end, we introduce another operation, which is like either Bob will measure or Bob will not measure. So this idea, let us see how this idea works. So if Bob does not measure, what he will do, he will simply reflect the received state back to Alice. Now, the idea is Alice randomly prepare a state. Bob can use some sort of a beam splitter, which half of times leads to the measurement of a state in which the thing ends there. However, if Bob does not measure, he simply reflect the state back to Alice, and Alice can then measure in the same basis in which she has prepared. Uh, but does it serve the purpose? So to check that, we assume we have an eavesdropper, namely Eve, who performs a C0 operation on the states traveling to and from. Uh, to understand this, we first consider the case in which Bob performs a measurement. So if Bob performs a measurement, so he keeps the state with himself. So the round in which Bob performs a measurement state travels only once from Alice to Bob. So over these states, if Eve performs a C0 operation in the computational base, she is getting the perfect correlation. So she know what is the output of a Bob, and so she knows what is the key which is being shared. However, if Alice sends states in the diagonal basis, so the effect of C0 is like one gets an entangled state. However, again, the point is because Bob is performing measurement only in the computational basis, this action of this eavesdropping will not be detected, and there will be perfect correlation between the outcomes of Bob and Eve. So again, Eve have the full information which is being shared. Uh, However, there is another possibility in which in which Bob does not measure and he simply sends a band. So that is equivalent to having a signal which first moves from Alice to Bob and then Bob to Alice. So it's a like a two-way thing. In that case, the Eve's action will also perform twice. So if we see that for the computational state, the first C0 makes a correlation between the traveling state and the state of Eve's system, and the second C0 simply takes that correlation away. So Eve does not gain any information, but again, there was no information which was being shared. The same thing we can see for the diagonal anti-diagonal basis. The first C0 leads to the entangled state. However, the second C0 makes the state as it was being shared. So the point is, the action of such eavesdropping does not introduce any errors, and Eve gained the full information which is being shared between Alice and Bob. So that is like that thing doesn't work out, because we should be able to detect the at least. So then we see how can we circumvent this problem. So to circumvent this problem, what can be done? Uh, Bob also sends his states back when he performs a measurement. So this is like adding the another thing. So now what the protocol is, Alice will randomly prepare one of the states. She will send this state to Bob. Bob will choose either measure or reflect. If Bob measures, he will send the post measurement state back to Alice. If he doesn't measure, he will simply send the state back to Alice. Now, if that is so, then that will be like acting C naught operation twice. So it will be, if we go back, so this was a round in which uh, Bob was performing a measurement. So when Bob sends the same subsystem back to Alice, that will be like acting a C naught again, and which reduces to the this kind of a transformation. Now we can see the final state which is shared between Bob and Eve is same as what was before Eve's interaction. So and Eve's ancilla is in the same state as it was before the interaction. So what it says, like Eve does not gain any information. So in this way, our this protocol is shown to be robust. Now, coming to the important part, which is the key generation rate. Now, because Bob is performing measurement only in the computational basis, so key will be shared only corresponding to this thing. And the rounds in which Bob simply reflects the state, those rounds will be used as a security check. So for to detect the presence of eavesdrop if there is. Now what we can see is like in half of the rounds are simply used for eavesdropping check. From the other half of the round, only 25% of the rounds are used for key generation rate. So we have only 25% of data that is being utilized for key generation, and we are discarding directly 25% of the data. Uh, so this discarding of a data, of course, puts a constraint on the key generation rate. Uh, Following this idea uh, is what I'm going to present now is my work of boosted quantum and semi-quantum key distribution. So what we are essentially doing, we are employing for this purpose qubits which are encoded in a higher dimensional state. So here I'm considering an example of a 4-level system. I'm having a 3 bases, B naught, B1, B2. B naught is simply the computational basis, and B1 is having a qubit in that particular 4-dimensional space. One can ask a question why I am interested in this particular idea, because that is because of the experimental fact, like which has been shown in many experimental works, like qubits can be prepared easily and with a very high fidelity, roughly of the order of 99%. So that is also an advantage from the experimental side. uh, But then the next question comes, in the last of the 2 examples, we have only 2 bases. Why we require 3 bases here? So that comes from the fact, like we do not want Eve to obtain any information without leaving out traces. So that can this particular choice can be seen from this thing. So if we have only 2 bases, let us say B naught and B1, then that is equivalent to ignoring this purple kind of states. So that will, in that case, Eve can perform a subspace measurement in 2, 3, and 0, 1 subspaces. So Eve will obtain the full information, and she will not introduce any other, because there is a no uh, correlation which is getting disturbed. However, if we take all the 3 bases, then one cannot find any subspace which is left and which Eve can exploit for the key distribution. So no matter which subspace now Eve exploits, she will bound to make errors. For example, if she employs this purple one, the error will be introduced in this red one subspace and the vice versa. Now coming to the protocol, again, like in the previous 2 cases, we are right now assuming the channel to be noiseless. Alice and Bob are supposed to be the intended participants who are sharing a key. Alice will prepare the states. Bob will again going to perform a measurement, and we are having a 3 bases. Of course, there will be a key generation rate, and in this case, that will be of perfectly 2 bits. But the advantage comes like even if the measurement is performed in different bases. So, for example, if we consider this particular thing, Alice is sending a state from B0, and let us say Bob measures in the basis B1. Even in this particular case, 1 bit of information is being shared. Why it is so? For that purpose, we can go to the examples of this basis. So what is happening? When Alice is sending a state from B0, let us say 0 is being sent, and Bob performs a measurement in the basis B1. So the outcome can be either 0 plus 1 or 0 minus 1. Now, Bob cannot with surety tell whether Alice sent a 0 or 1. But what Bob can tell, like either of the two states were sent. So it is like with the measurement of B1, Bob can tell which subspace was being used for the was being used, and this particular information act as a correlation between the two bases, and that is what we are being employing here. So whenever Alice sends a state from basis B0, all the three measurement in any of the bases leads to key generation rate. Whenever Alice send a basis B1, the two bases from the two different bases measurement, we are getting the correlation, and same holds for B2. Now this leads to key generation rate of 10 by 9, which is greater than 1 bit per transmission if one employ a 4-level system and 2 mutually unbiased bases. So we are getting an advantage here. Now, given this advantage, we move over to the hosted SQKD protocol and see whether we get some advantage here or not. Now, the steps of the protocol essentially remain the same as the one given by Boyer. The difference comes in the choice of basis. So Alice will again prepare one of the state from the 3 bases randomly. She will send it to Bob. Bob can randomly, in an independent of Alice, perform either measurement and send the post measurement state back to Alice, or Bob performs a reflex operation and simply send the state back to Alice. Now, whenever Bob reflects, it's like using this particular kind second operation. So whenever Bob reflects, those rounds will be used for checking the presence of an eavesdropper. However, in this particular case, in the case of SQKD, if Bob performs a measurement, what we see is one always gets a key letter which is being generated. So let us suppose Alice would have sent a basis B0 and Bob has measured. So Bob can unambiguously decide what state was sent by Ellie. So that, and since we are having a 4-level system, so this gives rise to 2 bits of information which is being shared. However, as in the last case, if Ellie sends a state from the basis B1 and Bob measure in the computational basis, Bob can determine which subspace from which subspace the state is being sent, and that leads to 1 bit of information, which because Bob can, because there are 2 sections of the subspaces which are there and that are sent randomly. So that is why 1 bit of information, and the same holds for basis B2. Now to see the advantage, we calculate what is the key generation rate, which in this case comes out to be 0.66 bits per transmission. To have a comparison, we also, if we employ SQKD with 2 mutually unbiased bases of a 4-level system, the key generation rate would come out to be 0.5. So this 0.66 is greater than that. So that is like an advantage. With this, we come to the conclusion. So qubits encoded in qubits, and that too with the tweaked key generation rule helps in increasing the key generation rate. It is much more advantageous in case of SQKD because whenever Bob performs the measurement, we have nothing to discard, so everything is being utilized. This idea, that will be very interesting to see how this idea behaves in case of networks, because ultimately one have to distribute information in it can be a single layered network or it can be a multi-layered network. So employing this idea in both quantum networks and the semi-quantum network will be worth of pursuing future studies. With this, I conclude my talk. Thank you.
Thank you. It was a wonderful talk. The session is now open for questions.
I have one question. Thank you for your talk. So, do you have any plans to consider decoherence in your calculations?
Okay, so yes, that we haven't done that yet, but yeah, that is what pursuing in the future directions, and that we will surely cover. And in fact, depending upon which particular degree of freedom one is employed, so using that particular decoherence model will be of much interest.
If I understood correctly, you are doing research in theoretical perspective, right? Not experimental.
Yes.
This is not an experimental exercise.
Yes.
Okay.
Yes, that is true, but we are having like because what we are employing are here higher dimensional systems. So depending upon whether one want to have a fiber based communication, or whether one want to employ the line of sight communication, I mean the free space communication. So a particular degree of freedom can be considered, because and there have been numerous studies which study the different decoherence model which are dominant in different degrees of freedom. So that will be interesting.
Thank you.
Thank you.